Okay, students, online students, can you see the slides, the screen?
Yes.
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 Thank you. Please, if you don't see the screen anymore, please let me know it, not by the chat, but just turn your microphone on and let me know it, because there seems to be some problem here with the camera. So sometimes it gets disabled, and I don't know why. So, okay, let me just see. Okay, so this is the other type of elementary function, which is the quadratic function. Also, quadratic functions are really important in calculus, because sometimes we don't look at the linear approximation of a function, but we look at the quadratic approximation of a function. So in many cases, we can understand almost all about the local properties. Local means near some point of a function, of any function, by just looking at the first order approximation, which is the linear approximation, and the second order approximation, which is the quadratic approximation. Basically, for some applications, it is enough to approximate a function with a straight line near a certain point. For other applications, it is more important to approximate at least with a quadratic function, which is a parabola, basically. That's why we must know everything about linear function and parabolas. So y equal to f of x in this case is defined as ax squared plus bx plus c. This is called a parabola. It is the example of quadratic function in one variable. A is different from 0, of course, otherwise we have a linear function. There are two different qualitative cases in terms of the sign of A. If A is positive, we have a so-called convex parabola or upward concave parabola. If A is negative, we have a concave parabola or sometimes downward concave parabola. Usually we will use convex for this one, upward concave, and concave for downward concave. Of course, the parabola is like this, right? So if it is downward concave, or concave, this means that it has a maximum corresponding to the abscissa of the vertex. Okay, so this is the vertex of the parabola. So the vertex of a concave parabola corresponds to a maximum point of the function, the point where the function reaches its top. And for an upward concave parabola, the vertex is the minimum. Okay? The point where the function reaches its minimum. It is possible to obtain explicitly, you will know that this is the abscissa of the vertex as a function or in terms of the parameters that characterize the equation of the parabola. Okay, minus b over 2a is the abscissa of the vertex of the parabola. We also know that there is another important quantities for these quadratic expressions. So let me just... can you please turn your microphone off? Thanks. Okay. This quantity is called the discriminant, and it has this expression in terms of the coefficients of the parabola b squared minus 4ac. If b squared minus 4ac is a non-negative quantity, then the function that represents a parabola intersects the x-axis. In general, in 2 points, in particular in 1 point, so it is tangent to the x-axis. if this quantity is exactly equal to 0. These intersections with the x-axis, you all know that mean that f of x equal to 0, which is an equation, has at least one real solution. In principle, it is possible to compute the solutions also when delta is negative, but we have to extend our set to the set of complex numbers, okay? We are not, for the moment, we're not interested in it. Here are some qualitative examples, but basically, what is parameter A? Parameter A controls whether it is convex or concave. If A is positive, then B basically controls whether the symmetry axis, which is this vertical line. Okay, so I should, yeah, but if I turn them off, then participants. If I mute them all, okay, the participants, and then I can see. Okay. Please, Wakar, can you please turn your microphone off? I can do it. Okay, but then he cannot make many intervention or.
Yeah, he can turn on again.
Oh, he can turn it out again. So what is my role as a leader? No. Very strong leader. Okay. Okay, so if A is positive, for instance, and B is negative, like in this case, then the symmetry axis is on the half plane of positive x, okay? Vice versa if B is positive. So B basically B jointly with A controls whether the symmetry axis is a vertical line lying on the half plane of positive x or of negative x, okay? What about C? If you look at the equation, C, you obtain here C if you set x equal to 0. So if you set x equal to 0, y is equal to C. So C represents the point of intersection. It is the intercept, basically. It's the point of intersection with the vertical axis, okay? So based on these elementary considerations, you can represent different cases for the parabola here, okay? I try to summarize, not all of them, but many of them, just to understand the basic mechanisms. If the discriminant, this quantity, is positive or 0, then you can compute analytically, you will know the two solutions, the 2 points of intersections with the x-axis. And this is the formula, very common and popular formula. Okay, just look at this. Graph here. Of course, this is what I mentioned earlier, Desmos. It's very friendly, you can learn it immediately. It is possible to write the equation. I can show you how to do that, just to let you know. I remove all of this stuff. I start again from the beginning. Of course, I can write a function. Just don't need to write y equal to. Just write 3x plus 2. And this is a straight line, okay? If I want to write a quadratic function and I want to add exponents, it's very easy to add the exponents. 3x squared is a parabola, for instance. But I can also write functions that depend on a parameter ax squared plus bx plus c, ax squared. Now, the system understands that there is a parameter here. So do you want to add a slider? Slider means that I can change the value of this parameter very quickly. So I add the slider. And the basic value is a equal to 1 plus bx plus c. So I must add 2 more sliders. Okay? And now what is the standard values for all these parameters is 1. So this means that now I'm representing the function y equal to x2 plus x plus 1, which is precisely this one. Let me see if everything corresponds to what we learned earlier. The point C is the intercept is equal to 1. Okay. A is positive and it controls the concavity, so it is upward concave. What about B? Remember that the abscissa of the vertex is minus B over 2A. Sorry, 2A. Okay, minus B over 2A is the abscissa of the vertex. The abscissa here is minus 0.5. You can see the value, okay? What about the discriminant of this parabola? Discriminant, we don't see any intersection with the x-axis. The discriminant will be negative in this case, okay? So it is b squared minus 4 AC, just right. And you see that the discriminant is actually negative, okay? So here, there is no x here, so no functions is represented here. You just add parameters, you assign values to these parameters, and you can see immediately the numerical result. What about the abscissa, the equation of the symmetry axis? The symmetry axis is a vertical line, so it has an equation of the type x equal to something, okay? So if I write here x equal to minus b over 2a, which is the same abscissa of the vertex, because the vertex belongs to the symmetry axis, of course. So minus b over 2a, I see this vertical straight line, which is the symmetry axis for the parabola. Then there is a way to change, whether you want thick lines or thin lines, the colors, various types of lines, and there is everything inside, okay? But this is just a way to see, you will see it's very useful to check the results of your exercises, to see what happens if something changes, etc. Okay? So basically, if I change now parameter C, and you can move the slider here or just change the value here. C equal, for instance, to minus 2, what happens? Now the parabola has the vertex on the negative part, okay? So it crosses the x-axis in 2 points, okay? So these are the 2 points. You can numerically see the solutions by clicking on the points, of course. So this is a situation in which we have the crossing of the x-axis. We can, for instance, change our A and make it become a concave parabola. For instance, if A is equal to minus 1, then we have something like this, okay? And we can, for instance, now put back C equal to 1, and we have a concave parabola that again crosses the axis in 2 points. So you can check, when you study something in theory, can see immediately in practice how functions look like, which is very useful. There is also a way to study not just, maybe also 2 variable functions, but for sure implicit forms, so written as 2 variable functions of 1 variable function. So you can also get the representation of a function written in implicit form. And there are many more properties that you can computing integrals and whatever, okay? So I think that graphically it's not possible to see 2 variable functions, but all other kinds of computations and visualizations are possible, okay? So I don't spend more time on the parabola, except letting you solve a simple exercise to show one thing. And then we will switch to power functions. Given the quadratic function 2 plus 1/2 x minus 1 over 20 x squared, find the maximum point of this function as well as its maximum value. Find the points of intersection with the x-axis, that is the solutions to the equation f of x equal to 0. And provide a graphical representation of this quadratic function along with the graph of this very similar linear function. It is 2 plus 1/2 x. So there is a quadratic term missing here, but for the rest, it is the remaining part is the same. Okay. Okay, the maximum, in general, we find maximum points using derivatives, but in this particular case, we know that it is the abscissa of the vertex, provided that the parabola is concave. The parabola is concave because A is negative. So, this is a concave parabola, these are the values of the parameters. This is the abscissa of the vertex, minus B over 2A, you can compute it, it is 5. Of course, it is the maximum point of this function. What is the maximum value? Now we distinguish, this is a general concept, between the maximum point and the maximum value. The maximum point is the abscissa, look at the picture here. The maximum point is the abscissa, is the value of x where the function reaches its maximum. The maximum value is the corresponding value on the vertical axis. Okay, it's the value taken by the function at x star. Okay, so the maximum value can be computed by replacing x star equal to 5 into the equation of the parabola, and we get 13 over 4. By the way, there is also a general formula for this because this is the vertical coordinate of the vertex, and we know that there is an expression in terms of A, B, and C. Okay, so you can also do that by just using the expression for the vertical coordinate of the vertex. Okay, the discriminant is delta, capital delta equal to 13 over 20. It is strictly positive. We will have two different intersections with the x-axis. We can compute the intersections by applying the formula. So this exercise is just a summary of what we need about the parabola. Okay. You can compute this by this formula. You obtain two values, usually written in this way with the plus minus here. So it's 5 times 1 plus minus square root of 13 over 5. These are the two values. This is the maximum point. Of course, the two values are symmetric with respect to the symmetry axis here. Okay. And I mean, anything else should be clear here. This is the representation of the results of our exercise. And this is the representation of the straight line of equation 2 plus 1/2 x. The exercise per se is very easy, but I use this to emphasize one thing. It turns out by using the calculus later that this is exactly the best linear approximation to the parabola at the point of abscissa 0. Okay? It is the tangent line to the parabola at the point of abscissa 0. If you look at the expression of the parabola and the straight line, clearly when x is very close to 0, the quadratic term, in this case it has a very small coefficient, okay? But even if this coefficient is 1, for instance, minus 1, the quadratic term doesn't matter. It doesn't matter because, for instance, 0.1 squared is 0.01, okay? So it changes very little with respect to the other part, okay? And you can see it very clearly from the graph. If you remain near point 2, you can, in some sense, replace your parabola with the straight line to study the behavior of this quantity when x changes close near 0. Of course, the larger becomes x on the left or on the right of 0, the more this term matters, up to the point where basically the qualitative behavior changes strongly. Okay. Now, if you increase x, the parabola decreases. This is just to show you what is the meaning of approximating linearly near a point. Clearly, there is very little difference near the point 0 and a large difference far from 0 in this case. Okay, so this is basically what we need about the parabola. Let me now go to the power functions. They are already I have uploaded already to the Virtuale yesterday. They belong to tomorrow's class, but of course we can start it today. Power functions. So in principle, this is not so easy. I mean, as the straight line or the parabola. There are some delicate points about power functions. What is the general form of a power function to us is of this type. Capital A is any constant. It can be positive or negative, times x to the power of r. X must be strictly positive. Next I will explain why. Of course, if r is 2, r can be any constant, any real number. Clearly, if r is 2, it is x squared. And in principle, x could also be negative. But if r, for instance, is minus 1, then it is a divided by x. Okay? So in this case, x, for instance, cannot be 0. If r is equal to 0.5, I have here a times the square root of x. And in this case, x must be non-negative. If you want to have a general expression for this function that includes all the cases, you must impose that x is strictly positive. Because if x is strictly positive, this is well defined for any constant r, for any real exponent r. Okay? This is why we usually set x strictly positive. In some cases, of course, x can also be negative or 0. In particular, if this exponent, which is a real number, any real number, is the ratio between two integers, positive or negative, and n in the denominator is different from 0, then we have an exponent which is basically expressed as a fraction, and we can write our power function, assuming a equal to 1 for simplicity, here the constant capital A equal to 1, x to the power of r is x to the power of m over n, so it is the nth root of x to the power of m. Okay? For instance, x to the power of minus 3 over 5, you know, negative exponent means 1 over the same power function with the positive exponent. 1 over x to the power of 3 over 5, so 1 over the fifth root of x to the power of 3, basically. Okay? Clear? The graph.